Hello and welcome. In this video, we're going to look at an application of the derivative called related rates. Now, essentially what we're doing here is just kind of scratching the surface of what you could use the derivative for. And in this case, we're looking at some sort of an equation where you'd find that in various different sciences, social sciences, whatever. An equation would involve two or more quantities, and the equation kind of describes the relationship between them. But if those quantities are not fixed with respect to time, if they are varying, then what we can use is the derivative, in this case, to sort of relate the quantities and how they're changing with respect to time. Hence the name related rates. We're looking at how the rates of change of quantities are related in a new equation. Now here I've got an example from chemistry, and we're going to be taking a look at three main variables that are related: pressure, temperature, volume. And the pressure times volume of a gas is equal to nR times the temperature, where N is the number of moles of that gas, which is like a quantity, and R is a constant. Now, what we're going to try to do here is, well, take a look at this equation with respect to time. You see, if two or more of these quantities vary with respect to time, then we can differentiate implicitly with respect to t. So applying the differentiation operator on both sides, we're going to take the derivative with respect to t. And don't forget to use our product rule on the left-hand side and a constant multiple rule, where we're going to treat n and r as just constants. And as a result, we end up with p times the rate of change of volume plus v times the rate of change of pressure equal to nr times the rate of change of temperature. Now, we call this kind of an equation a differential equation since it involves the quantities as well as their derivatives. And this is an equation that is now relating the rates of change of volume, pressure, and temperature at any given time. So you see here that we would need to know what the current pressure and volumes are, as well as maybe two of the rates of change in order to calculate the rate of change of the third quantity. So it's still an equation. There's a lot of different things we can plug in here now. So our variables are p, v, and t, but we also have dv dt, dp dt, and it's going to sound silly, dt dt, where we have temperature with respect to time. Well, now let's try applying this. Let's put some values into these equations and see what we can do with both the original equation as well as this differential equation giving us related rates. All right, let's suppose that I have half a mole of gas being held in a 3-liter container at a temperature of 273 degrees Kelvin. Well, right away, I could go back to this initial equation up here, and I could go and plug in that volume and temperature and a half a mole of gas and use the gas constant, 8.314, in order to calculate the given pressure. But of course, that's not really a calculus problem. That's a fairly basic algebra problem. We just plug some numbers in, and that's how an equation works. What we're going to do now is we're going to change the volume. And let's suppose we're increasing the volume from 3 liters to 6 liters. Now, that's not an instantaneous change. It's going to happen over 60 seconds. And let's suppose that during that period of time, you have enough other apparatus to keep the temperature constant. All right, well, what is the pressure halfway through this process? And at what rate is that pressure increasing or decreasing at that time? So, one of these is still using the original equation, and one of these parts is going to be using the differential equation. And so just take a moment and see if you can think about which equation we need to use for each of the two parts. In part A, if we're halfway through this process, then we should be halfway through the change of volume, halfway between 3 liters and 6 liters, and we can easily calculate that. Halfway through that change, we would be basically at an average of 3 plus 6. So 3 plus 6 over 2 ends up giving us 4.5 liters halfway through the process. Well, if we are just looking to find out what the pressure is, we know the volume, we know the temperature, we know how many moles of gas, we should just be able to plug this into the original equation, PV equals nRT, where we know volume, N, R, and temperature. Now, plugging those numbers in for V, N, R, and T, we find out that the current pressure is 252.19 kilopascals. And it's probably best to just express this answer in the form of a short little sentence. The purpose of expressing it as a sentence is kind of just there so you know really what you're interpreting by that number. Because we're going to be interpreting another number in part B, and it has a very different meaning. In part B, we want to find out at what rate the pressure is increasing or decreasing. Now, the moment you hear rate, you should be thinking about derivatives. And a derivative can mean many things. It can mean the slope of a tangent line, which, is more or less just a kind of a silly math problem. But it also means the rate of change. And it's the rate of change of a quantity that is so important to pretty much any other science, such as, in this case, chemistry. We want to know how things are increasing or decreasing. And so that is going to be where we use the differential equation. Now, in this differential equation, you notice that we have P and V as being quantities. dV by dt, dP by dt, and d temperature by dt, those are rates of change. So those are going to be with respect to time. One of these rates is already known. The temperature is being held constant. And if something is constant, then its rate of change is equal to 0. So in this case, again, this sounds silly, dt, just remember this is the rate of change of temperature, is equal to 0 since it is being held constant. But how quickly is our volume increasing? We know it's increasing from 3 liters to 6 liters. That's a change of 3 liters. And it's increasing. So if we wanted to, we could calculate that change in volume by subtracting final volume minus initial volume, 6 minus 3. And it's happening over the course of 60 seconds. So assuming that volume is increasing in a linear fashion, we can then kind of just use the slope formula, like y2 minus y1 over x2 minus x1, but applying that to volume. It's the change in volume, final minus initial, over the change in time, which in this case is 60 seconds. And we can simplify that fraction or express it as a decimal. So the rate of change of volume here is 0.05 liters per second. And the nice thing about using Leibniz notation, dV by dt, is that it tells you the units. It's units of volume, which we're using liters, per unit of time, which we're using seconds. And then, knowing two of the rates, and knowing the current pressure and current volume at this specific time, which is going to be 30 seconds of the way through the process, then we can plug these numbers in. Now, notice that we're not plugging in anything for time. We're simply plugging in the given quantities and their given rates of change at a specific time. So plugging in the current pressure of 252.19 kilopascals that we just calculated, and the current rate of change of volume of 0.05, and the current volume of 4.5 liters, since we're halfway through the process, that's multiplied by dP dt, which is the rate of change of pressure. And this question is trying to ask for that value. We want to know how quickly pressure is increasing or decreasing. So it's this derivative that we're actually trying to find a value for. That's what we're going to solve this equation for. And the right-hand side equals 0 only because temperature is being held constant. Otherwise, in order to find the rate of change of pressure, we would also need to know the rate of change of temperature. Now, we just rearrange this equation so we can get dP dt. And maybe I'll throw units in here as well so you can see how the units work out. You see that when we move our 252.19 times 0.05 to the right-hand side, we have to remember it's going to be negated. It's subtracted from the right-hand side. And we've got units of kilopascals times units of liters per second. That is divided by 4.5, which has units of liters. That cancels out the units of liters in the numerator, and we end up with units of kilopascals per second, which would be units of change of pressure by units of time. And if we wish to calculate that, we end up with negative 2.80. It's worthwhile to keep that negative sign in there so we can interpret what that means. In this case, if volume is increasing, pressure is going to be decreasing. So we should state that result. And this means that pressure is decreasing at 2.8 kilopascals per second. Well, in that example, we had one of the variables held constant, and like I said, if temperature was not held constant, then you'd end up needing one additional rate of change in there. And also notice, just because of the product rule, we actually have to know the current values of pressure and volume. The rate of change of pressure is actually dependent on how much pressure there currently is. And you can see that from this equation. However much pressure we have, this 252.19, if that was a higher pressure, then the rate of change of pressure would be faster. And if pressure was lower, the rate of change of pressure would be less. Same thing goes, we actually need to know the current volume at a specific moment in order to find out how pressure is changing. So sometimes you need to do a little bit of extra work with a related rate problem to find out all of the current values of quantities, so that you can use those current values and the current rates of change in order to find the unknown rate. At least that hopes to kind of unlock the door to related rates. It also kind of gives you at least a little bit of experience with what a differential equation is. Later on in integral calculus, when we have the ability to take an equation with derivatives and actually reverse the process and find how we can express those quantities as a function of time, then we can graph the rate, or we can graph the quantity with respect to time and see how things are changing. That's much further down the road. For right now, the nice thing about related rates is we can see how the current quantities and rates allow us to find the rate of change of something else unknown. Anyways, thanks for watching this video. I'll see you again in the future.